My name is James, and I'm a pure mathematician and lecturer at the University of Western Sydney. And I belong to the School of Computing, Engineering and Mathematics, and the more focused group, the Centre for Research in Mathematics. And the goal of this talk is to give you a flavour of some of the what I would consider exciting things that's in store for you if you choose to study mathematics further, and particularly at university. I'm going to try not to put complicated equations or anything that should be too scary to anybody, but we'll cover some fairly deep concepts and some fairly advanced topics. So, as the title suggests, the talk is about the concept of infinity, mostly from a mathematical perspective, and there'll be a small amount of philosophy thrown in for good measure, and you'll see later on what the beyond part has to do with it. So let's move on. This is the basic question that we're trying to ask, or trying to answer really. It's easy to ask it. What is actually infinity? And I'll try to give you some kind of idea of what it is. If you actually Google that question, you'll find some very interesting answers. Many of them are wrong, many of them are right, so it's always interesting to try and sift through information on the internet. That picture there is by the artist M.C. Escher, and it's one of my favourite ones. It has the sort of shape that we use to denote infinity, the sort of sideways 8, and it's also representing a Mobius band. That's the shape that the ants are travelling on. If you get your belt and put it on in the morning with a twist in one of the sides, then you find that you've got a Mobius band. It's a shape that has only one side. So the ant, if you follow it around, will end up, if it keeps walking, it'll end up below where it started, and then one more loop it will end up above. All right, the basic idea of infinity is the idea of things being unlimited. So here are three pictures that would appeal to different people. The one on the left would appeal to my one-year-old son, an unlimited collection of balls for him to jump in. The middle picture might appeal to some people, but it's sort of what seems to be academic work to some people. The picture on the right certainly appeals to me and probably everyone else. So the idea that I want to get across to you is the notion of what's come to be called Hilberts Hotel. A mathematician, David Hilbert, a long time ago came up with this idea and called this thing the Grand Hotel, and it's become known as Hilberts Hotel. So we're going to be talking about an infinite hotel, basically. Now, there are none of those on Earth, but this one is, as far as I can tell, the closest to it. A big hotel in Russia with about 7,500 rooms. Okay, absolutely massive. I did some research last night to check if it was still the biggest hotel, since I prepared these slides a couple of weeks ago, and there's a few things that could potentially rival it, but it's all a bit, you know, it's hard to tell if there's 500 rooms missing here or there. But like I said, Hilbert imagined an infinite hotel. So here we've got a hotel that has room after room after room after room that just never ever finishes. Okay, and let's accept these guys. So, so there's room 1, room 2, room 3, room 4, room 5, and it never stops, ever. All right? And here's how a mathematician would depict an infinite hotel. We get away the roof, the doors, all the extraneous features, and just concentrate on the bare essentials. Room 1, room 2, room 3, room 4, etc. And the dots mean that this just goes on forever. Okay, kind of like the X or Y axis if you've seen them in your education so far. Hopefully you have. So the story goes like this. On one particular day, Hilberts Hotel is completely full. All right. Not only is there an everlasting supply of rooms, there's a never-ending supply of people that are inhabiting each of them or occupying them. And a poor fella comes along and needs a room. And well, if there were only 9 rooms in the hotel, it wouldn't matter how you juggled the people around, there'd just be no way to fit him in, apart from sharing rooms, of course. But if we assume that he wants his own room, then there's nothing we could do. However, things can be a bit different with infinity, as we'll see. So here's what happens. checks if there's someone in room 1, room 2, room 3, room 4, and they're all full. So he gives up. And then he comes up with a plan. So here's what he does. Pretends he wants to talk to the guy in room 1, and then gets him out and nicks his room. Now the guy in room 1 is out in the open. And you can see that no matter how they swap, there's still one person missing. All right. He gets angry because he's missed his room. The guy in room 2 says, "Go and bug the guy in room 1." So he does. And he really shouldn't come out because he knows the trick, but anyway, he does. And now he's back where he started. So all is actually not lost, which is very strange. The hotel manager gets on the intercom and says to all of the people, all right, all of you come out, not just one. So all of them come out, and they really should be coming out at the same time, but I didn't have the software for that. And okay, now he says, all right, Mr. Red Sad Man, you go into room 1. And the guy from room 1 goes into room 2. The guy from room 2 goes into room 3. And each person just shuffles one room along. And everyone is back in a room, including the guy in room 1. So everyone's happy in this case. So we started with infinitely many people, added one more person, and we didn't end up really with more people. We had the same number of people that could fit this hotel. And that's the first sort of strange thing that we've discovered about infinity. Infinity plus 1 equals infinity. Okay? No other number is like this. You can't do 9 plus 1 equals 9. All right, what if not just one extra guest arrived, but 3? I'm quite sure that you'll know exactly what we should do in this situation, so we're just going to play the same trick. Everyone comes out. And what's going to happen? Well, of course, the 3 people are going to go into the first 3 rooms. And then each of the people before just goes into a room 3 higher than they were in before. So infinity plus 3 equals infinity. So that's the next piece of the puzzle. We're going to fill this box up with all kinds of facts about the arithmetic of infinity. Now, if it was infinity plus 11 or infinity plus even 1,000,000, I'm sure you know what the answer will be. And we indicate that by saying that infinity plus n equals infinity. Here, n stands for any old number, essentially, a whole number of people. But what about infinity plus infinity? What happens there? Well, what if not just 3 people or even 1,000,000 people arrive, but a whole extra infinite collection of people, which we usually represent by an infinite bus. All right? This infinite bus was photoshopped, I'm pretty sure. This one was not photoshopped, but it was drawn. And there's a hotel on the left, drawn with a bit of artistic license. It's a bendy one, and so is the bus. And I had to Google this, but the woman in the middle of the picture is apparently saying, "Meet me at midnight in room infinity." All right. So there's the mathematical way to depict an infinite bus. Now, we know that the first person could be fit into the hotel. We've seen that the first 3 people could be fit into the hotel, and you can imagine the first 1,000,000 could be. But once you've done that, there's still a lot of people on the bus that haven't been put in. So a more subtle trick is required in this case. We start again by letting everyone out of the hotel. But now we've got 2 infinite collections of people. And the trick here is very, very clever. We essentially shuffle these 2 lines. So imagine you've split an infinite deck of cards into 2 piles, and you just shuffle them together, kind of like that. Okay? We just take turns. This is called interleaving the 2 collections of people. All right? If you go like this, everyone gets their seat. So basically what you can see is that the black stick figures are occupying all the odd numbered rooms, and the red figures are occupying all the even numbered rooms. So infinity plus infinity, well, we didn't get any more people. We could still fit them into the same hotel. So the answer to that question is infinity. Infinity plus infinity is infinity. Right? These are very strange equations. You couldn't rub out infinity and put any other number there. 7 plus 7 is most definitely not equal to 7. Now, another way to say that infinity plus infinity is to say that infinity times 2 is infinity. All right? We learn multiplication by first of all doing addition. And if you do 7 plus 7 plus 7 plus 7 plus 7 5 times, we call that 5 times 7, rather than writing out 5 sevens and 4 plus signs. All right, what if there were 3 buses? I'm sure as before you can perfectly well guess what's going to happen, or not even guess, but work it out. Everyone comes out of the hotel, and then we shuffle the 3 sets together. So we're going to put the 3 people that were in the first position in the hotel and the buses in first. Then we're going to put the 3 people who were in the second position of the hotel bus and second bus, and so on. So we put them in groups of 3s. And of course, you'd know what to do if we had 7 buses. We just go in groups of 8 or whatever it is. So infinity times 3 is also infinity. More sort of madness. Like I said, if there are 8 buses, you get the same thing. So infinity times any whole number is still going to be infinity. And you can sort of see what the pattern is. We're generalizing slowly and then kind of going to the extreme. So the next question, obviously, is what is infinity times infinity? What if there were infinitely many buses, each of which have infinitely many people? Now, this is a real conceptual stumbling block for a lot of people. Okay, we now believe we can fit the first busload of people in, and then we could fit the second busload in. We could even fit the first million busloads in, but we've still got a lot of buses to go. And before I press play on this little video, which is, I think, the last video we're going to look at, I want you to all tilt your head 45 degrees to the left, and let me see if I can do this the right way. So it looks like I'm doing it to the left, even though I'm doing it to the right. Tilt your head to the left, 45 degrees, and rather than seeing infinitely many rows of infinitely many people when you look at the buses, see a pyramid. It's like an infinite pyramid, like this, extending off in an unlimited fashion towards the bottom. So keep that in mind as you watch this. Okay. The first step is always, when trying to fit people into the hotel, get everyone out. And now just tilt your head to the left, and slowly, shortly you'll see that the pyramid is still composed of infinitely many rows, but each row has finitely many people. The first row has only 1 person, the second row has 2, the third row has 3, then 4, the next row has 5, even though the first person of that row is missed out because I haven't drawn the 5th bus, but it goes like that. And now we empty the pyramid by taking people out row by row. The first row goes up here, then the 2 people from the second row go next, then the 3 people from the third row go next, and you can see what the pattern here is, of course. So because each row now of the pyramid only has finitely many people, each person will at some point exit the bus. So eventually we'll just have 2 rows of people, the black people from the hotel and the red people from the buses. And we know perfectly well what to do with 2 rows of people. We just interleave them, or we shuffle them together and take turns. So infinitely many buses somehow managed to fit into the hotel, even though it was completely full. It's madness, basically. So the thing we've proved there is that infinity times infinity is infinity. Okay, a million times a million is most definitely not still a million. It's a much bigger number, but infinity times infinity doesn't get bigger somehow. All right, I'm writing that in a different way now. Infinity squared equals infinity. Okay, 7 times 7 is written as 7 squared. And I'm not going to do a video for infinity cubed equals infinity. I hope you'll just trust me on that, although when I say trust me, I mean for now. You should go and look this up on the internet and find something that will convince you of it. The reason I didn't do this is because basically I'd have to have somehow drawn infinitely many car parks, each of which has infinitely many buses, each of which has infinitely many people. But you could still fit them into the hotel. It's really a bit of a miracle. More generally, it's the case that infinity to the any whole number whatsoever is still infinity. And as we progressed in the previous examples, the next question to ask is, what is infinity to the infinity? All right. Here we have to be quite a lot more clever, or we have to rely on the work of someone else who was extremely clever, Hilbert. In fact, it's more a guy called Cantor, whose name I'll put up towards the end. So to address this problem, we're going to look closer at the passengers on the bus. So in everything so far, you've just seen stick figure clones. Okay. Now, each of these clones, well, they're people. Okay. There's Albert, Brad, Claire, Davina, and so on. Okay. Eventually, we get to someone starting with Z, but we can just use other names. Now, imagine a parallel universe or an alternate version of reality, where you woke up today, everything was the same, but instead of having cornflakes, you had rice bubbles. Okay. And imagine in a parallel universe, the same people got up in the morning, got onto the infinite bus, but Albert and Brad just decided to swap seats. That's the only difference. Okay, then it keeps going Claire, Davina, Ernie, and so on. All right. You can imagine another alternate universe where this time Claire is in the front seat, Albert is now in the third seat, Ernie is in the fourth, even Waldo is making an appearance now. And imagine a universe for every possible way that the people could have sat themselves on this bus. Okay, it's the same people in each bus, but it's different arrangements from one bus to the other. Now, how many buses are there here? Well, one way to think about that is to ask the question, how many people could we choose to sit in the first spot? Well, infinity, because that's how many people there are. Now, once we've chosen the person to sit in the first spot, how many people could we choose to sit in the second spot? Infinity. There's still infinity. How many could we choose to fit in the third spot, fourth spot, fifth spot, sixth spot? It's infinity is the answer to all of those questions. So the number of buses is infinity times infinity times infinity times infinity forever, no stop. So the number of people altogether, or the number of possible buses is infinity to the power of infinity. And the question becomes, would it be possible to put all of these guests in the hotel? Okay, all of these buses arrive, can we fit them in? And the answer, very strangely, is no. Okay, everything we've tried so far has worked, but this does not work. Okay, and in fact, I'm going to try and convince you that not only is that the case, but an even stranger thing is the case. Even if somehow we were able to fit an entire bus into each room, or even if we were allowed to do that, we still couldn't fit all the people into the hotel. All right. Now, how do you do something like that? How do you demonstrate a concept like that? Well, we use what we call proof by contradiction. Okay, this may seem a bit crazy to some of you younger students, but you'll see this in time, even at school. You assume the thing that you're trying to prove is false. Okay, you say, all right, let's just say you're right. Let's say you can actually fit them in. And then you somehow show that that leads to something absurd. Okay, sometimes you might be able to show that 1 + 1 = 3. And then you have to reject the thing that you assumed. But anyway, we're going to assume that we can match all the buses up to all the hotel rooms. So let's put this all in a table. All right, let's say we've got room 1, room 2, room 3, and we've somehow managed to match those rooms up to all the buses. All right, now here a bit of notation comes in, and I hope this isn't too scary, but all it's really meant to indicate is that the second bus is called B2. Okay, it's not a banana, it's a bus. And if you look what's inside the brackets, you'll see there's something with a 1, something with a 2, something with a 3, something with a 4. So here, B2 in brackets 4 means the fourth passenger on the bus B2. All right? And what we've assumed is all of the buses are in that list. But what we're going to do is somehow show that even though that's supposed to be the case, it's not the case. We'll show there's still a bus missing. So there's the buses. And I'm going to describe another bus to you that isn't in that list somehow. And I'm going to call this one B. I suppose I could have called it B infinity if I wanted to, but anyway, let's call this one B. And I'm not going to tell you who these people are. I'm not going to say B1 is Albert and B2 is Wally or anything like that. I'm going to tell you that B1 is someone different from the first passenger on the first bus. Okay? If the first bus had Albert here, I'm going to put anyone but Albert in the first position on B. The second passenger on B is going to be anyone but the second passenger on the second bus, and the pattern continues. Okay? There's a slight amount of subtlety as to whether we can do this, but I'm not going to go into technical details. Let's just say, though, that this bus has all of the people on it, so it must be in our list because we assumed our list had everyone. So which bus is it? Is it B1? Well, it can't be the first bus because we made sure that it didn't have the same person as the first passenger of B1. So it's not B1. Similarly, it's not B2 because if you look who's sitting in the second seat, they're different. It's also not B3 or B4 or B5 or any of the buses. So B is none of the above. Okay? But remember right at the start we assumed that we had put all of the buses in the list. And that is a contradiction. They're all in the list, but there's something missing. That can't be the case. So let me just recap what we've done here. We've assumed that we could match all the buses up to the rooms. This led us to an absurd contradiction. So we conclude that our original assumption must have been faulty. It's not the case that we can match the buses up to the rooms. So in other words, there are more buses than rooms. Now, how many buses were there? There were infinity to the infinity, and that means that infinity to the infinity is bigger than infinity. All right? Let that sink in for just a minute. The answer to that question is that infinity to the infinity doesn't equal infinity. It's bigger than infinity, okay, whatever that might mean. So I'm sure you'll notice the odd one out in this box. You probably thought that everything was going to equal infinity, but this doesn't. So the question that should be on your, or in your minds now is, what does it actually mean for something to be bigger than infinity? Isn't infinity the biggest thing? Well, the other way to ask that question is, what on earth is going on? So we've just seen, I hope you're convinced. If you're not, by the way, go and look it up back on YouTube. Pause the video, think about each step, because mathematical proofs just work from one step to the next. You don't have to take the whole thing in the first go. But anyway, I hope you believe me that infinity is less than infinity to the infinity. And with more work, you can show that that is even less than infinity to the infinity to the infinity, which is less than a tower of 4 infinities, okay? Which is less than a tower of 5, less than 6, less than 7, and so on. So there's actually an infinite chain of bigger and bigger and bigger infinities, okay? But that's not all. Here's an infinity that's bigger than all of them, okay? We take this infinity, add that one, add all of the things together, and you get something that's even bigger, okay? It's bigger than them all. And there's more, okay? Now, there's so many of these different infinities that we use a special symbol for them. This is a Hebrew letter. In maths, we normally use Greek letters, but this is an aleph. That's a Hebrew letter, and aleph 0 typically stands for the smallest infinity. It's what we've been using the sideways 8 for. Aleph 1 is the next smallest infinity, by which I mean the smallest infinity other than aleph 0. All right? I've sort of indicated that there's no biggest infinity. Given any infinity, you can find a bigger one. The list basically goes on forever, so there's infinitely many infinities. You might be wondering how many infinities. If there's infinitely many of them, which infinity is it that says how many of them there are? But that's a very interesting question. Now, I'm going to end this talk with an unsolved mystery. I've told you a lot of answers, and I'm going to tell you a question that we are not in a good position to answer. You'll notice that I highlighted aleph 1 red, but I didn't highlight infinity to the infinity red. Okay? Both of them are bigger than infinity, the blue infinity. So we know that aleph 0 is less than aleph 0 to the aleph 0. That's just this equation translated into the new notation. But we also know that aleph 0 is less than aleph 1. Okay? Now, Aleph-1, I've said, is the smallest infinity beyond the first one. Okay? The question is the green kind of infinity the same as the red kind of infinity, or is it a bigger one? Okay? Basically, where does this infinity belong in this list? Is it here, or is it something further along? Okay? And, as I said, this is an unsolved mystery. We actually don't know the answer to this question. But it gets worse than that. It's an unsolvable mystery. Okay? We don't know the answer to it, but we do know that we will never know the answer to it. It could be the answer is yes, it could be the answer is no, but we will never ever be in a position to know the answer. And unfortunately, that's just the way it is in mathematics sometimes. You can't just write this on an exam when you don't know the answer. Sorry, teacher, this is an unsolvable question. But in this case, that's just the way it is. So I have one more slide, which is probably more for the benefit of you guys to look up the YouTube video later on. It's got a list of some interesting topics that you could look up for further research if you're interested in this. The first 6 up the top have some interesting paradoxes. Sometimes the Hilberts Hotel is called the infinite hotel paradox because it just seems weird that you can keep fitting more people in. Here's some even more strange paradoxes, even going back to the Greeks more than 2,000 years ago. And below you'll find the names of some important mathematicians. Especially I'd encourage you to look up Georg Cantor. I didn't have any opportunity to talk about him, but he's responsible for a lot of the ideas that we discussed today. And over here are some philosophers. Graham Oppy is actually an Australian philosopher. He's down in Melbourne. That's an extremely good question, and I wish that I had a lot more time. I don't need an infinite supply of time, but yeah, infinity minus infinity can't be defined, actually. And it just so happens that my first published paper in philosophy is on that exact question. Basically, if we go back, let me see if I can find it, to this hotel here, if everyone checked out, then there's no one left. So infinity minus infinity seems like it should be 0, right? But what if everybody above room 3 checked out? Then there'd be 3 people left. So infinity minus infinity seems like maybe it should be 3. Okay, or what if all the people in even numbered rooms checked out, 2, 4, 6, 8? There'd be infinitely many people left, the people in the odd numbered rooms. So maybe infinity minus infinity should be infinity. Okay, but all that does is show that infinity minus infinity can't be defined. We can define addition of infinite quantities, but we can't define subtraction of infinite quantities. And some philosophers think that that presents some kind of problem, but really it's not my view that it does, and it's not the view of most philosophers that I know of. Certainly Graham Oppy is someone who argues against such bizarre ideas.